Lab 3, Black Hole and Orbits. The purpose of part 1 of this lab was to first determine the mass of the black hole and model the orbit of a star around it. The purpose of part 2 was to find the velocity needed for a ship to make a figure-8 orbit around both the planet and the moon. Through calculations and computational models using Newton's second law, I was able to find a reasonable mass for a black hole. I was also able to find a velocity for the spaceship that was affected by both the force from the planet and the force from the moon. I did this through using the gravitational force formula to find all the different forces, making a computational model for the orbit of the ship, and testing what velocity gave me the desired output. The main physics ideas. The momentum principle in Newton's second law has been very helpful for this lab. It lets you calculate momentum from multiplying mass times velocity. Solving for momentum also allows you to find the net force, since another part of the momentum principle is that change in momentum divided by change in time is net force. A gravitational force is the force felt by the system due to the mass of the source object. Multiple times in this lab, we had to find the force of gravity between two objects. In the formula, g is the gravitational constant, m1 is the mass of the source, m2 is the mass of the system, and r is the distance between the objects, and negative r hat is the direction of the force. This formula allows you to find the force of the source on the system. In order to find r, the distance between the objects, you have to calculate the position of the system minus the position of the source. It is important to include all the forces acting on an object in your FNet calculation. We also use the position update and velocity update formulas derived from Newton's second law to show how the changes in force affect the path of the system. In experiment part 1, we had to make a model for the orbit of the star around a black hole, and then find the average mass of the black hole. Here, the system is the star, the source is the black hole, and the initial conditions are that the position of the black hole is at the origin, and the position of the star and velocity of the star are a given random value. And here's the code for part 1. Using the given initial velocity of the star orbiting and mass of the star, I calculated the momentum initial and final for the star. Then, using the calculated initial and final values, I found the change in velocity and change in momentum. And using Newton's second law, we know that the net force is delta p over change in time, 1 day. Then, with the net force, I was able to calculate the parallel force and perpendicular force for the star. Then, using the gravity force equation, with r being the distance between the star and black hole, and knowing the total force on star, I could calculate the mass of the black hole. This happened in a loop, so there was a mass output for each day in the orbit. And here is my final model. And after adjusting the scale of the arrows to show the correct magnitudes and direction of each force, the orbit was complete. I took the average of each black hole mass output to find the most likely mass of the black hole, 9.14 times 10 to the 33rd kilograms. The average mass of a black hole in the real world is between 10 to the 30 kilograms and 10 to the 40 kilograms. My found mass value is in this range, which means my results are fairly accurate. In experiment part 2, we had to find the velocity needed for a spaceship to make a figure-8 orbit around the moon and the planet. System 1 is the moon, and source 2 is the planet, and system 2 is the ship, and source 2 is the moon. And the initial conditions are that the position and velocity of the moon is given, and it starts to the right of the planet. The position of the ship is also given, and it starts on the moon. The velocity of the ship, we had to test different values until a model was found where the ship's orbit did not crash and was dependent on both the moon and the planet. And here's the code for part 2. I was given the initial position and mass of the moon, ship, and planet, so I was able to use the gravitational force equation to find the force between these objects. First, I found the net force for the moon by treating it as the system and the planet and the ship as two different sources, and adding the results of the force-gravity equation to find the FNet on the moon. I then repeated this with the ship as the system and the moon and planet as two different sources, adding the force results to get the FNet on the ship. I then used the velocity update and position update formulas for the moon and the ship to be able to plot their orbits by plugging in their respective FNets. And here is my model for part 2. After calculating the net force on the ship and moon and finding their respective orbits, I tested different initial values for the velocity of the ship. I found that a figure-8-esque orbit was achieved when the initial velocity x was 2.55 times 10 to the 4th meters per second, and the y was 2.46 times 10 to the 4th meters per second. These values allow me to see the influence of both the moon and the planet on the motion of the ship. Sources of error could possibly be human error in the mathematical calculations, or maybe applying the formulas incorrectly. We also don't account for other possible forces and interactions that occur. In conclusion, it is possible to find a reasonable mass of a black hole in a system with a computer model. We are also able to use a computer model to model the effect of different gravitational forces on a ship's orbit. So what does it mean and what if? The first question, momentum is mass times velocity, but does not factor in a change in time. Net force, however, factors in a change in time. It is the change in momentum over the change in time. This is from Newton's second law. And for the second question, you would need to be able to include the force of the black hole on the moon and the force of the black hole on the planet and the force of the black hole on the ship. You would need to factor in the black hole to the net force calculations. The dominant interactions would depend on the largest mass of the objects interacting. The end.